as you can tell by the title of the video and the words at the top of the empty black screen, I'm going to be talking about the fundamental theorem of calculus, but for Calculus 1. So this is the one you will learn in Calculus 1. If you're a Calculus 3 student, get out of here. I have another video on the fundamental theorem of calculus for Calculus 3 if you're curious. But essentially, they're two in the same thing, but Calculus 1 is a specific, less general version of it. So what does the fundamental theorem of calculus states? Well, it states that if you have an upper bound and a lower bound, you must solve the integral like so. So you plug in the upper bound into your antiderivative and subtract another antiderivative, but this time the input is the lower bound. So let's talk about what the antiderivative does. Let's say you have some function, doesn't matter. I just drew a curve. And you plugged in, let's say you found the antiderivative for this function right here. It's just arbitrary function, it's just squiggles, doesn't matter what the function is. It's just a very general way to explain it. But let's say this bound up here is 4, right? So if you found the antiderivative and you plugged in 4 into your antiderivative, so your antiderivative for this function is, let's say, capital F of x, and you plugged in 4, f of 4, then the result of your antiderivative, so the area you would get is this blue area, from 0 to 4. So if you plug in 4 into your antiderivative, you would get the area from 0 to 4. Not in all cases. In trigonometric functions, it works a little bit differently. That's why you want to plug in zeros even. But let's worry about this for now. So if you plug in 4, you get the area from 0 to 4 of your function. And if you plug in, let's say, if you plug in, use a different color. Say if you plug in 1 into your antiderivative. So let's erase this. And let's say you plug in 1, then you will get the area from 0 to 1. Well, what if you wanted to only find the area from 1 to 4? What if you only cared about the area from 1 to 4? Well, what you can essentially do is simply subtract f of 4, the area from 0 to 4, from the area from 0 to 1. And when you do that, you get left off with the area from 1 to 4. So that's basically the core concept of the fundamental theorem of calculus. Basically, you want to subtract the lower bound antiderivative from the upper bound antiderivative. But that's really basically it for the fundamental theorem of calculus. I'm going to give you guys a little more information on why the arbitrary constant, or the plus c, goes away for the definite integrals. And I'm also going to be explaining why it kind of works a little differently for trigonometric functions. The logic still stays the same, of course, right? Because these are rules, these are theorems. It's not just going to be, oh, there's an exception, out in the open, you know. But let's say you had some function like this, and this function is negative sine of x. Well, the antiderivative of negative sine of x would be the cosine of x. So that means cosine of x tells you the area under the curve from some point to 0. And let's say that our bounds were pi over 2 and 0. Well, from what I stated previously, okay, so pi over 2 would be here on the graph, on one of the troughs of negative sine of x. From what I stated previously, pi over 2 should give you the area from 0 to pi over 2. It doesn't in the case for this trig function. 0 actually gives you the area properly, but basically what's happening is if you plug in pi over 2 for your antiderivative cosine of x for the function negative sine of x, so let's say we plugged in cosine of pi over 2, our upper bound first, and we subtract it from the lower bound, we actually get the function 0 minus 1, because the cosine of pi over 2 is 0. So although we use pi over 2 for the upper bound, it won't give us the area from 0 to pi over 2 for negative sine of x. You need to plug in the 0. So never forget about the 0. That's why I'm saying this. Even if you have exponential functions as well, like let's say you had e to the power of x as your function, 0 has a value. If you plug in 0 into an exponential, you get 1. So keep that in mind. Don't forget about zeros. Make sure it's good practice as well. Make sure you plug in the lower bound all the time, even if it's 0. 0 doesn't always cancel out. And now we can talk about the arbitrary constant. So essentially what happens is if you take the integral of some function, right, you get an antiderivative, and you have the arbitrary constant, right? But what happens is if you have the fundamental theorem of calculus, you put a plus c here and a plus c here. Essentially, the antiderivative arbitrary constant will both be the same. But this negative actually distributes into f. So if you write f of b plus c minus f of a minus c, since this minus distributes into the c just cancels out. Because when you have an antiderivative, the arbitrary constants will always be the same, right? You take the antiderivative of some function. It doesn't make sense to have this be plus 2 and this to be plus 3 when it's from the same function. So the arbitrary constants cancel out. That's why you don't need to put the plus c for definite integrals. But, that's really it for the video. I gave more than enough information for you guys to solve definite integrals. So, as always, if you have any questions, put it down in the comment section. And if you found this video helpful, consider subscribing. I would greatly appreciate it. Thanks for watching.